On Feistel ciphers. So the first of the two talks is going to focus on linear cryptanalysis aspects, and it's a paper by Betül Aşkın-Özdemir, Tim Bene, and Vincent Reimann. So enjoy the talk and think of some questions for later.
Thanks. Welcome to my presentation about multidimensional linear cryptanalysis of a class of Feistel cipher. It is already mentioned. It is a joint work with Tim Bene and Vincent Reimann. In this talk, I will give a brief introduction firstly, then I will continue with details about generic multidimensional distinguisher. And I will explain how we can extend this multidimensional distinguisher to efficient key recovery attack. I will also summarize our theoretical and experimental findings. Linear cryptanalysis is one of the most important cryptanalysis techniques against block cipher, and it is based on probabilistic linear relation between input bits and the output bits, and this probability is equal to is close to 1/2 if f is a strong function or permutation. Then we can define the distance as 2 times difference of this probability from 1/2, which is called correlation of linear approximation. And one aim to find linear approximation with high absolute correlation. In the case of key alternating ciphers, functions are parameterized by key, and keys only affect the correlation sign. In this example, key is XOR to a branch of algorithm. Then if we know the masked key here, we can define correlation sign. And this property is important while obtaining a multidimensional linear distinguisher. And multidimensional linear cryptanalysis, this is one of the extension of standard linear cryptanalysis. In this technique, we use multiple linear approximation instead of one, and these approximations form a vector space. And multidimensional linear approximation can be turned into linear distinguisher, multidimensional linear distinguisher, using probability of linear projection of input and the output. Basically, if we know the correlation of approximations, including their sign, we can define probability distribution using this equation. It is obvious that one difficulty is key dependency of correlation sign. And it can be solved by statistical test. In the unknown correlation sign case, chi-square test is recommended. If we know the correlation signs, we can use likelihood ratio test as an optimal test statistic. And both data complexity of both tests are inversely proportional to capacity, which is sum of the squared correlations. And as you see here, data complexity of likelihood ratio test better than chi-square test because of this extra multiplication. So if you want to reduce data complexity, it is good to continue with likelihood ratio test. Feistel ciphers are well-known and widely analyzed block ciphers. And in this work, we focus a class of Feistel cipher. Specifically, key is added to the algorithm before the round functions. And there are several algorithms based on this structure. For example, isostandard cast is based on this structure. Note that if we eliminate the key from this trail, we can define correlation sign. Since we obtain key-dependent trail, then we can find probability distribution. And as you see this figure, this trail exists for Feistel ciphers. If we fix input mask to 0 for each round, we can obtain key-independent trail. And as you see here, output mask is the same as the input mask, which means this is iterative trail. We can extend this trail. To obtain generic multidimensional linear distinguisher, we need to replace this round function with random function. Then we have to compute correlation trail using random function. And correlation of trail can be computed product of correlation of active round function And C here represent correlation of random function from f2 to the n to f2 to the n. And correlation of random function is 2 to the negative n over 2. As I said before, to find the data complexity, we need to find capacity. Since we use all possible u value, it is enough to compute squared correlation by 2 to the n to get capacity. Then, as I already said, data complexity is inversely proportional to capacity. Then it is approximately equal 2 times 2 to the n times rounded down r over 2 minus n. And note that we rounded down r over 2 because for the odd round numbers, we can start with 0 u mask instead of u0 to keep active round function as small as possible. In this table, we summarize and compare our result with the existing best generic distinguisher results. As you see, we improved 2, 4, 2, 3, 5, and 7 round Feistel ciphers. And for the 4 and the 6 result, we get the same result with the existing results. But these are the rough estimation. To find exact value of the data complexity, we can use statistical test. And likelihood ratio test is powerful test if we know both distribution. And in our case, since we obtain key independent trail, we know sign and corresponding probability distribution. Then we can use likelihood ratio test. And here, pair real represent actually distribution of some of the right half of the input and the left half of the output, actually active part of the input and the output. And P ideal represent uniform distribution. To find success probability of our attack, it is enough to compare test statistic with threshold value for given data complexity and fixed false-positive rate. And our aim to maximize advantage, which is given absolute difference of success probability and false positive rate. And during the analysis, we realized that if the real includes 0 for some z values, we can say that these values don't occur in the frequency table. Then we can immediately decide this is not a real cipher. Then we can find advantage of attack using this equation, actually using number of 0 values and data complexity. To verify our theoretical finding, we apply our technique to CAS 128 and Lucky 91. Both of them are based on our target class of Feistel cipher. These figures represent round function. In CAST, there's a 5-bit key rotation at the beginning, and there are 3 different round functions according to order of operation. And these operations are modular addition, modular subtraction, and XOR. In Loki, there is no key rotation, and all round functions are the same. And block size of both algorithms are 64. Key size is 128 for CAST and 64 for Loki. I already mentioned about capacity of generic case. Then we want to analyze our target algorithms in terms of capacity, actually to check randomness of the round functions of their target algorithms. And according to this equation, capacity for 3-round, 5-round, and 7-round Feistel ciphers should be 1, 2 to the negative 32, and 2 to the negative 64, respectively, because block size is 64. As you see, CAST behaves like a random function according to capacity result, but Loki is not that much. To find, to compute capacity efficiently, we use fast Fourier transform. First, we encrypted all possible 2 to the n values using target algorithms. Then output values, output occurrences are stored in different vector. Then FFT is applied to this vector. Then to find some of the squared correlation, sum of the squared of pointwise product of these vectors is computed. To find the exact value of the data complexity, we did some experiments. This table represents 3-round LR distinguisher, and these results support our theoretical findings. If we focus 1 point, for example, if we use 2 data, we can distinguish low-key with advantage 0.6. If you use more data, you can distinguish a cipher with higher advantage. And this table represents 5-round LR distinguisher results. Similarly, if we focus on 1 point, for example, this one, if we use 2 to the 35 data, we can distinguish test with advantage almost 0.9. We also extend this distinguisher to key recovery. To do this, block cipher is divided into 2 parts. One part is used for distinguisher, other part is used for key guessing. And correlation for each key guessing can be computed by partial decryption. Without any trick, time complexity is Q times 2 to the n. Q represents data complexity. But the test statistic can be computed by using part of the input and the output. So the test statistic can be computed by matrix vector product. So in MATC method, this matrix is obtained based on key and this partial information about input and output, and also vector z, occurrences of these z values. And data complexity become Q plus 2 to the 2n. But general, this matrix has a spatial structure. It is circlant matrix. So it is enough to compute only one row. So we can improve also this complexity to Q plus n times 2 to the n. But we cannot apply this technique, FFT-based key recovery, to our technique because of the memory complexity problem. So we prevent this distinguisher and keep right part as constant. Then compute test statistic depend on key dependent constant. And M based on this key dependent constant and Z values, which is sum of left part of the input and the left part of the output. And W occurrences of these Z values. We also use FFT method to compute this matrix vector product. Actually, we compute this matrix vector by taking the pointwise product of FFT of first column of this matrix and FFT of this vector, followed by inverse Fourier transform. And this table shows our result, generic key recovery results and existing best results. For the 2n key size, we improve time complexity of key recovery for 6-round Feistel cipher. And for 4n key size, we improve data complexity of key recovery for 5-round Feistel cipher. For the 6 rounds, we have 2 results because we use both 3-round distinguisher and 5-round distinguisher. And for 7 and 8, existing results are better than ours. One of the reasons is they use meet in the middle attack technique. And in this table, we compare our experimental results, but not that our experimental results of time complexity better than existing one. Because in the meet in the middle attack, I already mentioned about there is a key rotation in the round function of cast. And in the meet in the middle attack, they need to guess this 5 more bit for each rounds. But in our case, we have to guess these 5 more bits only additional rounds. So our time complexity results for 7 and 8 round cast is better than existing result. We also improve, as you see, data complexity and time complexity results reduce round cast versions. And this table summarize our result and existing results. As you see, we also improve key recovery result on 4-round lucky and 6-round lucky. And for more than 6 rounds, our attack complexity of our attack higher than brute force. As a result, in this work, we obtain generic distinguishing attack on a class of Feistel cipher using key independent multidimensional approximation. These multidimensional approximation allow us to use likelihood ratio test because they are key independent. And we extend the distinguisher to efficient key recovery using fast Fourier transform based method. Then we also apply our technique to verify our theoretical result. And our theoretical and experimental finding shows that our attacks lead to significant reduction in data or time complexity in many interesting cases. Thanks for your attention.
Thank you. Do we have any questions from the audience?
Thank you for your presentation. I have a question. If you're using an FFT method, does it mean you have to have like specially crafted plain text for this to be evaluated, or it's really something different?
Can you repeat it again?
The plain texts, do they have to be of special form, like
No, actually,
to be an FFT domain, or?
Actually, it is enough to take left part of the input. We don't have any spatial structure. And this Z value depends on this left part of the input and the left part of the output.
Okay, I just wonder because sometimes you have recovery of polynomials and stuff not using FFT, but like on any domain, you just have to pay an extra logarithm factor. And based on that, I wonder if you can do also something interesting if you don't have restrictions on the plain text anymore.
For our case, we don't have any restriction.
Okay, thank you.
I think there was a second question over here. Maybe I give my microphone.
Thank you. So please go to the page 9. Yeah, maybe that's my misunderstanding, but say this for the example, the 2 rounds and the result for the 2 rounds and 3 rounds, this table shows that the attack complexity for both data and time is 1.
Yeah.
And from the probability security perspective, that 2 round Feistel is probably secure against the non-plain text attacks up to the birthday bound, and the 3 rounds for the chosen plain text attack. So is there, I just wondering what's the gap between these,
Yeah, actually this result directly comes from actually this equation.
Yeah.
So if you have 2 or 3 rounds, it will be always 1. So data complexity is approximately equal to 2 to the n minus 2 to the n, which is 2 to 0 and 1.
Sure, yes, and this attack is generic.
Yeah,
so
generic.
Each F function is assumed to be
random, and
you don't impose any assumption about the F function.
Just
so
these are random, and then data complexity becomes like that.
Yeah, in that case, the classical Luby-Lakoff theorem combined with the Eben-Masura result shows that tells that this Feistel, say 3 round is secure against the attack, any attack against the data using the up to the 2 to the half of n queries. So maybe there's some gap or between my understanding and the actual attack pattern. I need to clarify. Thank you.
Thanks a lot. So let's thank the speaker again and welcome the next speaker. So the next work is by Xavier Bontin and Virginie Lallemand. It will focus on boomerang analysis, I believe. And Xavier is giving the talk.
Yes. Can you hear me? Okay, yeah, but that's much better. So yeah, thanks for the introduction. And indeed, we will discuss boomerangs. So first of all, we do a quick introduction on boomerang and distinguishers. How do they work? How can we find them? And the starting point will be differential distinguishers that you probably all know about. So we start with a difference, we encrypt it, we obtain a new difference. And if we find a good pair alpha beta such that the transition probability is high enough, we have a distinguisher and we can do a lot of fun things from that. So now for boomerangs, this is slightly different, but with similar ideas. We start with a difference, we encrypt it, then we add some other differences to the output, we decrypt it, and in the end, we might obtain the same difference at the beginning. We say that the boomerang returns. And if we have obtained this event with a high enough probability, so given some alpha and delta, we also have a distinguishers. So now there's a question of how can we find good values for alpha and delta to obtain a good distinguisher. And there has been a first approach on boomerang constructions, which is to split your cipher in two parts that they call E0 and E1, and you start with some good differentials from each part, so with probability P and Q. And then you can start with the first input of your first difference on E0. You encrypt it, so with probability P, you will obtain a difference beta in the middle. Then you encrypt it through E1 to obtain the full cipher. And then if you add a difference delta that corresponds to the second differential, when you decrypt it, with probability Q, you will obtain gamma in the middle, and the same for the other side. So the cost here is PQ square, and if you have this property in the middle, the last difference will be beta. And so you can also come back to the beginning, and hopefully with probability P, you obtain alpha. And so the overall probability of this construction will be P square Q square. However, the main thing to have in mind is that here we assume that all the events are independent. And actually, we can see that in the middle, all differences share the same values. So the independent assumption is pretty optimistic. And so from this construction, there has been a more advanced way to construct boomerangs. And notably, there's been the sandwich framework. And the idea is very similar, but instead of splitting your cipher in two, you would split it in three with an EM in the middle. And this middle part will have to tackle all the dependencies between the differentials. You still have differential trades on the outer part, and you will use another approach to compute the probability in the middle. That is either through experimental computation or with some ad hoc formulas and so on. And more recently, there has been a more systematic approach to boomerang analysis that has been proposed, which we call the BCT approach. It started with an analysis for one round of an SPN, and it shows that we can do that actually in a systematic way and reduce the analysis of the boomerang probabilities for one round to the analysis at the S-box level, which is of course much more amenable than just a large state, a function of a large state. So this was the first approach on one round of an SPN. And since then, there has been a lot of variations and updates with this kind of approach that can target either more rounds of a cipher or a different kind of ciphers. And in this talk, I will focus on such a variance with the case of quadratic phase-tail ciphers. So if I want to do a boomerang on a phase-tail cipher, and I will start with one round of a boomerang, I can write down what it means for a boomerang to come back. And what I will obtain is the following equation that's on the slide. And we can see that this equation is actually the second derivative of the round function at the differences of the boomerang. And this is extremely interesting because if the round function is quadratic, then its second derivative has degree 0. That is, it is a constant. So we have actually only two cases. Either the two differences are compatible, the second derivative will be 0, and then the boomerang returns with probability 1, independently of the state value, or they are not, and in this case, the probability will be 0. So this is a completely deterministic behavior, and in a sense, it is a case where the independence assumption is the most wrong. There is nothing probabilistic here, and we have a direct dependency between the differences. So now that we have this generic idea, we decided to apply it to some concrete ciphers, and we identified two. That is the Catan and the Simon families of block ciphers. So they come with various block sizes and key sizes, from 32-bit block size to larger versions. In this talk, I will mostly focus on the 32-bit block size versions, which also have a 64-bit keys. You have the round function on the slide. The main thing to have in mind is that they are both phase-tail-like, meaning that the previous equation applies, and that the round function is quadratic, meaning that we have the all or nothing behavior over one round. So this means that from the round function, we can actually compute an explicit equation that involves the differences in a boomerang, and this equation must be satisfied for the inner differences of a boomerang for it to come back. So now we decided to revisit previous boomerangs that have been proposed in the literature for Catan and Simon. We found that there was quite a few work on that, and we identified 20 distinguishers on these ciphers among 6 articles. What was interesting is that they all used the naive p-square q-square probability analysis. So we decided to check them using the previous formulas. So in order to do that, we did that using the characteristics that were available in the paper, and we simply checked whether the top characteristic was compatible with the bottom characteristic according to our equation. So the result depended on the amount of information and details that was available in the different papers, but there was essentially 3 cases. In some cases, we were able to prove that all pairs of differentials are incompatible with each other, which means that the overall probability of the event that was considered to make a boomerang is actually 0. So it shouldn't work at all. In some cases, it was inconclusive, either because we didn't have enough details or because it wasn't so clear-cut. We couldn't directly determine what happens. And in some rare case, actually, all pairs are compatible with each other, which was the case for the Simon 48 boomerangs. And after doing these verifications on the trades, we decided to do some experimental verifications. So really run the cipher, compute experimentally the probabilities from the outer differences of the boomerang. So of course, we did that for high probability boomerangs. For the low probability, we fixed some bits in order to increase the probability and still have an estimate. And in this case, we obtain essentially 2 results. Either the distinguisher doesn't work at all, the actual probability is 2 to the minus n, so we don't distinguish anything from that. Or in some cases, when the stars align, the distinguishers actually works much better with a much higher probability than the predicted probability from the model. So overall, with these previous boomerangs, we have, in all cases, an inaccurate prediction of the probabilities, and more often than not, this gives us distinguishers that just don't work. So we decided to make new distinguishers for Simon and Catan, and hopefully more accurate one. So in order to do that, we developed a bit-oriented SMT model that makes boomerangs for Catan and Simon. And the idea is still built around the sandwich idea. So we split our cipher in 3 parts, E0, EM, E1. For the E0 and E1 part, we only have 1 characteristic, which will have probability p square or q square. This is the part where we assume everything is independent. and it's essentially a differential behavior. And we will have a middle part, which is in charge of tackling all the interactions between the trail, in which we allow truncated trails. So some bits can be unknown, but we enforce for all the rounds in the middle that the boomerang constraints are satisfied. And so in terms of optimization, the game will be that we will try to minimize the number of output bit differences to fix in order to still be able to prove that all the differential pairs are compatible with each other, and overall the probability of the boomerang will not be 0. So we applied that, first of all, for Catan. So here are the summary of our result for Catan. So we see here that we've chosen more or less arbitrarily a cut between top, middle, and bottom part. We fiddled with it, and these kind of values seem to work pretty well. We obtained boomerang for 140 to 152 rounds. So the round function is very weak, which is why we have a very slow decrease in probability. So here it is the logarithm of the probabilities, so 2 to the minus 17 and so on. And we also experimentally verified all of them. And so we see that we have some slight variations of up to a few bits, but in all cases, they actually work, and the model predicts fairly well the actual probability of the boomerang. So now we can compare that with previous works on boomerangs. And there is only one boomerang still standing for Catan in previous work. It is on 140 rounds. And we can see that the estimated probability for the boomerang was 2 to the minus 22, and the actual probability is around 2 to the 16. So for 140 rounds, we have a boomerang that's very similar, but our model is more accurate. And of course, we can also can tackle much more round. And now there's a question for this boomerang on whether or not this changes anything for the security of Catan 32. And unfortunately, there's a much better attack based on a meet-in-the-middle approach that attacks 206 rounds, and it attacks it in single key, because these are related key boomerangs that we have. So as it's more than 50 more rounds than our best distinguishers, it doesn't change much for Catan, unfortunately. So now I will move to the Simon cipher. And before delving into our result, I will discuss a bit some variations on differential cryptanalysis, namely rotational XOR differences. So you have your standard differentials, when you XOR two values, you obtain your difference. And for rotational XOR, it's almost the same thing, but one values will be rotated here by 1, but you can rotate by other values if you want. And the XOR of the two will be your rotational XOR difference. While the two are slightly different, you can pretty much construct the same things with normal differences and rotational XOR differences. And in particular, you can make boomerangs with rotational XOR differences. So here in the slide, you have the standard boomerang with standard differences that we all know of. You have a rotational XOR boomerang. So this is a boomerang where the top trail uses rotational XOR differences, and the bottom trail also uses rotational XOR differences. And recently, there was a new variation that was introduced, the rotational XOR differential boomerang, where the top trail uses rotational XOR differences, and the bottom trail uses normal differences. So these are slight variations, but they are still pretty close. And in particular, for Simon, we still have the all or nothing behavior and some equations that must be satisfied in the middle for the boomerang to work. And so we made a model that is actually able to produce boomerangs for all three of these models. So now here are the results for our boomerang distinguishers on Catan. So we have many distinguishers from up to 12 rounds, where we are in standard related key, and 13 in rotational XOR related key, where we have a probability 1 distinguisher. I found it interesting because to the best of my knowledge, this is the maximal number of rounds that tackled by neural distinguishers in related key for Simon. So here we do that with probability 1. And we can reach up to 19 rounds with rotational XOR differences. And so as with Catan, we have the predicted probability and the experimental probability, and we can see that it matches really well our predictions, especially for rotational XOR distinguishers, where it's almost perfect. So now that we have some distinguishers, we decided to do some key recovery and took the 2 longest distinguishers we had, an 18 and 19 round, and make an attack from it. So we start from one of the distinguishers that's presented in the picture, and we added 3 rounds of key recovery above and below. And note that the rotational XOR distinguishers we have must start at round 3, so we were pretty lucky with that. I spare you the details of the computation of the attack, but we obtained 2 attacks, one on 24 rounds that requires 2 to the 31 data, and one on 25 that requires the full codebook over 4 keys, that is 2 to the 34 data. And now, if we compare with previous attacks, to the best of our knowledge, the previous best attack was a linear attack against 24 rounds of Simon 32 in single key that requires the full codebook. So what we obtained is both the first 24-round attack that doesn't require the full codebook, but less than that, and the first 25-round attack against Simon 32. So now, to conclude, so we found many issues in most boomerangs against Catan and Simon. We made some new and more accurate boomerang distinguisher, and we used them to obtain the first attack against 25 rounds of Simon 32 in related key. And I will conclude with some advices to cryptanalysis. First of all, don't be naive with boomerangs, otherwise you may have some issues. And if you can, if the block cipher has a block size small enough, or if your probability is high enough, verify experimentally your distinguishers. This way you will avoid many pitfalls. Thanks for your attention.
Thanks a lot. So where are the questions for Xavier? Let's maybe start one with which follows quite directly from your conclusion here. So you recommend not to be naive with boomerangs, and I guess this also applies to other combined attacks like differential linear. Do you have any concrete recommendations or best practices that cryptanalysts should follow when they think they found a new boomerang attack?
Well, there's always, if your probabilities are high enough, just try it experimentally and see how it works. And if it doesn't work, you might have an interesting new theory that might be publishable at FSE. And otherwise, I would suggest doing something similar than BCT approach, so some kind of systematic probability analysis, at least for a small number of rounds, like we do in boomerangs.
Any other questions? Ah, there's one over there. Mike is coming.
So a quick question. You mentioned earlier that some of the boomerangs did not work and some of them had much higher probability.
Yes.
Does the average is correct? Does it follow the analysis?
Well, it's an average over different boomerangs, so I don't think it makes much sense. But on average, the boomerang doesn't work. I would say.
The question is whether the average probability works, meaning I guess that the conditions, so let's say there are 6 contradictions or 6 conditions. So only one out of 64 boomerangs would work, but then the probability would be increased by 64 times 64 versus the 63 out of 64 that doesn't work.
The issue is that the number of conditions you have depend both on the cipher and on the activity patterns of the trade. So I don't have any statistics about that. But yeah, I think the fact that some boomerangs work much better is a sort of counterpart from the fact that in some cases it doesn't work at all.
Thanks. Anything else that popped up? Otherwise, I'd say enjoy the break, which lasts until, how long do we have a break now? Until 2, so it's lunch break.